Hello guys, in this chapter we're going to study rotational motion. So first we'll be going through some major concepts involved in rotational motion, like the moment of inertia, the angular momentum, and all that. And after that we'll be going through a few important questions from JEE point of view. So let's start with rotational motion.
Okay, so I'll start with a very basic example to let us know what is the importance of rotational motion. Now, for example, let's take a small wheel. Now, if we consider normal translational motion, and suppose if I'm putting two forces over here, one F over here, another F over here. In the normal translation motion, we'll see that the force is zero, and so the work done will be zero, blah blah blah.
Right.
So, but now, since it's a big body, and if you practically see it, and these two forces will make the wheel rotate.
Okay.
That means something is happening around here.
Right. So even if the forces are equal and opposite, the body will move.
Yeah.
Wow.
So this is something new for us.
Yeah.
Now we are moving on to big bodies.
Right.
This is what rotational motion is all about.
So in translational motion we were dealing with very small bodies.
Right.
They are concentrated at the center of mass. Right.
Okay, so now since we are doing a completely new kind of motion, we need new values. So here we'll see some analogous values. Like for translation motion we had mass m. Yeah. So similarly over here we have I, which is the moment of inertia.
Okay.
Now next, similarly we have the different values, the omega, which is analogous to the velocity in translation motion, the alpha, which is analogous to the acceleration, the L, which is the angular momentum, which is analogous to the momentum P, the torque, tau, which is analogous to force F. So these are the basic quantities which will help us define the entire rotational motion.
Right, and they will help us in relating rotational motion with translational motion, and that makes things easier.
Easier, very, very much easier if you remember these codes.
Right.
So now we'll go on explaining one quantities as we go ahead. So let's start with the moment of inertia, which is the mass analogous to rotational motion.
Okay.
Here we'll see that moment of inertia is defined as sigma mi ri square. Here all these i's are the different particles which belong to the body, and r is the distance from the axis. Since it's rotational motion, there will always be an axis involved. So this r will define the distance of the particle under consideration from the axis. Now suppose if we have a continuous body, we can't use the sigma sign. So there comes in the integral. We take small sections and we integrate it over dm. Now there are situations wherein if you see, we might have to find the moment of inertia about different axes. There might be some situations wherein we know some moment of inertia but we need it around some another axis. So there come in the different theorems like the parallel axis theorem and the perpendicular axis theorem. These theorems will help us. For example, if I have some random body and the center of mass is over here, and I know the moment of inertia through this axis, and I want it through some another axis which is over here at a distance d. So here comes in the parallel axis theorem. We can use the parallel axis theorem, which says that the moment of inertia of a body about any axis is equal to its moment of inertia about center of mass plus its mass into the distance of the axis from the axis passing through the center of mass, uska square.
Okay. So there can be a number of axes possible through the center of mass, right? But we take the parallel one.
Yeah, we need to take the parallel one because the theorem itself is named parallel
axis theorem, right?
You might need perpendicular axis sometimes. Okay. So for that we have the perpendicular axis theorem.
Okay.
But we need to remember a very important point over here. Perpendicular axis theorem is only applicable to 2D bodies. It's not applicable to 3D bodies.
Okay, so this caution should be...
This should always be taken care of. Perpendicular axis theorem is very simple. It says that the moment of inertia about any axis which is perpendicular to the surface, like now since it's a 2D body, it will be a basic surface, any surface. So Iz will always be the axis which is normal to this surface, this axis. And Ix and Iy will always be the axis which are perpendicular to each other and on this body.
Right.
Okay, so this will be our perpendicular axis theorem. Now if you see finding moment of inertia of every body every time is not much that easy. So we have some basic bodies over here whose moment of inertia we should remember by default. Because if you see, most of the bodies around the world can be made by combining these bodies. And
right, so these are standard results.
Yeah,
they need to be memorized.
Yeah. So here we have the ring which has the moment of inertia of mr square. We have a hollow cylinder, the moment of inertia for which about an axis passing through its center is mr square. We have the disk for which the moment of inertia is mr square for an axis which is perpendicular to its surface.
Right.
Next we have the solid cylinder.
So the axis is also important, right? The moment of inertia will change with the axis.
The moment of inertia was defined as sigma mi ri square. So the ri is very important over here, which defines the distance from the axis. That is why we need to always remember the moment of inertia as well as the axis.
Okay.
Next we have the solid cylinder, through which the inertia is mr square for the axis passing through its center. The next thing which we have here is the hollow sphere, for which the moment of inertia will be 2 by 3 mr square for an axis passing through its diameter, one of the diameters.
Okay.
Next we have the solid sphere, for which the moment of inertia will be 2 by 5 mr square for a similar axis as the hollow sphere. And next the rod, for which the moment of inertia will be ml square by 12 for an axis passing through its center. Here we can, for example, very easily use parallel axis theorem to find the moment of inertia of this rod for an axis passing through its edge, which will basically be very simple, which will be ml square by 12 plus m into this distance, which will always be L by 2 as usual, and that will be L by 2 square. So this will easily give us the moment of inertia for the axis which is on the edge of the rod.
Right.
Next we move on to a very new concept which is known as the center of gyration. In the translational motion we had learnt about the center of mass, wherein we could concentrate all the force which we were applying on the body. So here we have center of gyration, where we can concentrate all the torque which we apply on the body. Now what is this torque? It's a new concept here. Again, something which is synonymous to the force which we apply.
Okay.
So let's move on to torque. Torque is basically you can say the moment. It's known as the moment of force, and that's why it's also written as force into the distance, which is the distance from the axis. Okay.
Right.
And as we know that force is always equal to mass into acceleration. Similarly, as I was analogous to mass and alpha was analogous to acceleration, we can also write torque is I into alpha.
Okay. There's a lot of symmetry, right?
Yeah, a lot of symmetry. If you remember the analogous situations, you can easily find out these formulae. You don't need to remember anything new around here. Next, we move on to equilibrium conditions. As we know that for translational motion, the equilibrium is there only when the total force applied on the body is 0. Similarly, over here we'll see that the rotational equilibrium occurs when the torque applied on the body is 0. And a similar concept as in translational motion we had the linear momentum. Here we have the angular momentum L, which is defined as I into omega. As in the translational motion we had mass into velocity. And a different way of writing down the angular momentum is R cross P, where R is the vector joining the axis to the point of which we need to find the angular momentum.
Okay.
And P is the linear momentum of that point.
Okay. So it's the cross product.
Yeah, it's the cross product over here. Here we see how the linear terms are combined with the radial terms to find the angular momentum.
Okay.
So, and now one of the most important things which we need to remember is dl by dt is equal to tau, which is very similar to dp by dt equal to force. But here again we need to remember this very properly. This is a basic conservation law, you can say, angular momentum conservation.
Right.
For example, if you have a body and its moment of inertia increases somehow. Very simple example. If I'm sitting on a chair with my hands close to me and rotating around, my moment of inertia is very less because all the mass is very close to the axis. Now if I move my hands apart from me, my moment of inertia will increase because the mass is moving away from the axis and the R increases. So here the moment of inertia increases, and so the omega will have to reduce because the torque on me is 0. No one is applying any force on me.
Okay.
So you see.
So is there any conditions required for this law to be applicable, or is it as in we can apply this on any question, on any scenario?
Yeah, apply it anywhere. Wherever you have a 0 torque, no action.
Okay, 0 torque.
Zero torque, because dl by dt is equal to torque. If your torque is 0,
Okay,
your
so
L is constant.
conservation of angular momentum, right?
Right.
So whenever torque on a body is 0, angular momentum is conserved.
Right.
Like when we say when the force is 0, linear momentum is conserved.
Right. And next concept which we need to know for studying a motion is the energy which it puts in the body.
Right.
Because now, as we saw in the wheel example, we were applying force, but according to translation motion, there was nothing happening. But rotational motion showed that the body was moving. So it also gives us what is the energy of that motion. So this energy will be defined by half I omega square, which is again very similar to half mv square.
Right.
So now if suppose we have a very complicated body which is also rotating, which is also moving in a straight line, how do we go about analyzing that body? We just simply come and connect both the motions and find a single motion. For example, if you need to find the angular momentum of a body which is moving in a circle and also moving ahead, so basically what you do over here is you find the angular momentum of the center of mass. If suppose I need to find the angular momentum at this point, the angular momentum of the center of mass will be this velocity into the distance. This will be the distance. So this will give me the angular momentum of the center of mass of this body, and to that I'll add the angular momentum of this body about the center of mass, because this body is also rotating, which will be given by mass into r cross v. R cross v is the angular momentum.
Okay.
So this gives us the angular momentum of this entire body about some external point.
Okay. So this seems like a very complicated formula, but I hope it will be clearer when we go through the questions and
sure.
we see the applications,
Right.
So next we move on to some questions from the chapter rotational motion.